dear friends. This time we're going to have a very exciting lecture. We're going to talk about different thermal qualities of water, also how these thermal qualities of water are applicable in the kitchen, in our environment, in the climate. We're going to see why it is so good to live in the coastal areas, regarding the breeze that is coming always, and more and less constant temperature. And before we start, I'd like to encourage you, if you're not familiar with the questions that we discussed before completely, please go and revise them. And also for those that watch this lecture for the first time, you're not going to do justice to yourself and to me and to the material that we're discussing if we start watching it straight from now. There will be a terminology and a chemical specific terminology that is going to be difficult for you to follow, and you may get bored and you may not get the best of it. So if you get into this lecture straight by chance, please go from lecture number 1 and carry it on through all the lectures. But now we're going to study how the water takes its 3 phases: solid, gas, and liquid, and what it takes to go from phase to phase. All of these physical properties are due to what we studied before, and it will just overemphasize and it will illustrate even much more what we studied before. So as you see here on the graph, there are the 3 phases of water. We're going to study that there is another one which is kind of mixture between gas and liquid, but if that's something new, don't worry, we're going to study it in detail, so you're not going to miss anything. Now look at this graph. Now don't get scared of graphs, don't get scared of terminology that we're going to use. There is a solid molecules. We say that, as you can see there, the molecules are ordered in the hexagonal shape. Then with very sturdy, strong hydrogen bonding. Then we're gonna have liquid, and then we have gas phases. This is the 3 major phases. Now if we plot the temperature on the x-axis and pressure on the y-axis, we're gonna see some very interesting phenomena. This is what actually we're going to study just now. Now all of us know that one atmosphere is the atmosphere of the sea level, the pressure of the air at sea level. As we go higher, the atmospheric pressure gets lower. And we all know that at 1 atmosphere, at 0 degrees, look at it, 0 degrees, 1 atmosphere, the water start melting. In science, melting is substituted with fusion. It's called fusion. Then after, if we keep on the atmosphere at 1, that means the atmospheric pressure we keep at 1, but to increase the temperature by 100 degrees, we're going to reach the boiling point. We're talking about sea level. At boiling point, the water start evaporating. All right. So this boiling point is called vaporization in scientific language. So the melting point is called fusion, and this one is called vaporization. Now, but there is a lot of combinations between pressure and temperature. Now, if we rise up the temperature, the water is going to stay gas at 1 atmosphere, that's for sure. If we reduce the temperature below the fusion point or the melting point, is going to stay solid. But now some interesting things going to happen if we're going to reduce the pressure. Now look at it now. If we reduce the pressure at almost 0 degree, and just little bit above 0 degree, we're going to go to a point which is called triple point, which is very interesting point. The triple point is the point where, as you can see, water exists as a liquid, as a solid, and as a gas. This is very interesting situation, because actually you're going to see the water boiling, freezing, and being liquid at the same time. Look at it. Obviously this inside of the vacuum container where the air is sucked and the temperature is getting 0.01 degree, and now you see what's happening now. The ice is there. You can see some. It will take some time because the pressure is so low, the water start evaporating as well. So this is the triple point. You can see bubbles start forming. And you've got ice, and then you've got also liquid. Now look at it. Boiling, freezing, and liquid water at the same time. See? This is the amazing triple point. Can you imagine if you stick your fingers there, if you can, because you won't be able to open the vacuum apparatus, you're gonna feel quite cold because the water is just around 0 degree and it's boiling. It's ice and liquid and boiling at the same time. That's triple point. Now look at it, what's going to happen if we increase the pressure at this point just below 0. If we increase the pressure, what's going to happen is the water is going to get melted when the pressure gets like 200 bars, 200 atmospheres. It's going to get melted. That never happened. That is only unique property of water. There is also a few other compounds that displays such a property, where when the pressure gets higher from solid it goes to liquid, like methane and others, some other organic compounds, and that's incredible, and that actually makes the property of the water that we always emphasize when it's a solid. It's less dense, so it's going to float on the more dense phase. That means the liquid phase. Why this happen? Simple. We studied last time that the hexagonal structure of the ice takes more space. Now when we apply more pressure, we start breaking these hydrogen bonds and the water becomes liquid with pressure. See, we start breaking, so it starts getting liquid. Also, this is, as I said, watch out, it's unique property of water. If we see another liquid and another substance like carbon dioxide, say for example, is liquid above approximately 5 atmospheres and above minus 57 degrees. It's liquid. So we need a lot of pressure and we need a little bit lower temperature. But that's not impossible. That's okay. Now look at it. If I increase the pressure, from liquid is going to turn solid. It's completely different than the one that we had before. Look at it if we compare the two graphs. See what's going to happen. look at it now. The water curves to the left, carbon dioxide turns to the right. This is why when I apply pressure from this temperature, say, up is going to turn to solid. While I apply pressure when it's a solid, it's going to turn to a liquid. That's incredible. Now look at also at another property of water. And this is also very, very, very interesting. You see, to look at it. This is also available to carbon dioxide. Now, when we increase the temperature, 300, 400 degrees, right? And we increase also the pressure at a critical point, 374 degrees and 218 atmosphere, then above this point, we're going to have so-called supercritical fluid. That's the critical point, and that yellow place of the graph is called supercritical fluid. Why is it called supercritical? Because beyond the supercritical, the critical point, the supercritical liquid behaves both as a gas and a liquid. Gas and liquid together. See, same thing we see at the graph of carbon dioxide, and there we got supercritical fluid, and that has a very practical usage in a lot of industries. This supercritical fluid. This is the graph, and you can see how unique is the graph of water. Another point that I want you to watch very closely, another place of the graph, more precisely say, is that there is a place where from solid the water from ice turns to a gas directly without getting into the water phase. So if the pressure is low, and the temperature is under this triple point, then what's going to happen is when we increase the temperature, see, then we're going to have so-called sublimation. From solid, it turns to a gas, and vice versa. If we decrease the temperature at this pressure or at any other pressure below the triple point and the temperature, then what's going to happen is going to turn from gas directly to solid. Such a behavior is familiar in our daily life. If you heard about dry ice. Dry ice is exactly, look at it, at 1 atmosphere, minus 78 degrees, the carbon dioxide directly turns from ice to gas. This is why it's called dry ice. It doesn't get wet, and it's used in a lot. It's also in a lot of industries. So here's the dry ice, and you can see it's not melting immediately. It's evaporating, turning to the carbon dioxide. There was a tragic accident where some guys, young guys, took dry ice, and in the closing indoor swimming pool, they throw kgs of dry ice. The effect, it's very nice, it's spectacular. They throw it in the swimming pool indoors, and 25 of them died because you can't smell carbon dioxide, and actually it kills you. It's terrible. They lost their life because of that. So this is the sublimation. The reverse process is called deposition. All right, deposition. And if we look at another point, this graph, is that the boiling point of water, when the pressure is lower, gets also lower. Look at it. At 80 degrees, at say 0.8 atmospheres, it's approximately 80 degrees, around there. All right. So the water start boiling at 80 degrees when we're high in the mountains. So it's not reaching 100 degrees, so the food is not cooking properly. We need more energy. Vice versa, if we increase the pressure above 1 atmosphere, the boiling point is rising. See now what's happening with this rising of the boiling point. Now the water starts boiling not at 100 degrees, but start boiling, say, at 120. And this is what exactly the pressure cooker is doing. And this is why it cooks the food much faster, because increase the boiling temperature, it means it stays still liquid. It doesn't turn to vapor. So it doesn't disappear. Anyway, in the pressure cooker, there is no way to disappear because it's pressured. It's closed. But it's increasing the temperature of boiling, and in this way, the cooking takes less time than if we cook it without the pressure. So when the pressure is high, the boiling temperature gets higher. Now, you may ask a question, is there a place where the water, we can see actually sublimating, goes from ice directly to gas, and we can watch it with our eyes? But there is a place where we can watch that. There you can see this crater on Mars, and there you can see there is a lake, ice lake. And there is this piece of ice there. And what's happening, the pressure of atmosphere of Mars is below 100 of our atmosphere. So what's going to happen if the pressure is below 100 of our atmosphere? The water is going to sublimate. That means he's going to turn from ice directly to vapor. And that's what's happening at Mars. Exactly what on Earth is happening with dry ice, carbon dioxide. On Mars, this is happening with water. So what's happening with this lake? When the temperature is relatively high, the water turns straight to vapor. And when the temperature is low, the water deposits back into this ice, and the ice piece gets bigger and bigger and bigger. But you'll never see water, liquid water. So that's at a point. There is a point where the water will get directly from solid to gas phase. And we can see that on Mars. Sublimation also may be observed on Earth, but in a very limited instances. It's not so drastic like here on Mars. So what's happening on Earth is we can see a phenomena like ice and snow or frost actually slowly disappearing in very cold weather, right? Then it starts slowly disappearing, but very slow. It's almost imperceptible. So this is what I said. On Earth, we can't see it in such a drastic proportions like we see it in Mars, simply because the pressure of atmosphere is 100 and more times than the one in the Mars. But still, we can see it in a limited instances. And also, what you can see, it's if we put it in a deep freezer, you can see if we have frozen food and it's not covered with plastic, you can see you start getting freezer burn, so-called freezer burn. Now, we can see again here the care of the creator, because we need to have the right pressure for water to exist as it is now here, liquid. Otherwise, it will just evaporate in space like in Mars. There is no liquid water. We need right pressure. Now, if we got too much pressure, we won't exist. Biology won't exist if there is too much pressure. And also, if we got too little pressure, the water will fly away. Also, obviously the pressure is caused by gravity, so we need to have correct size of the planet. Now, if we go to the moon, which is approximately 60 times smaller than the Earth, so what's happening even say, for example, we take all the water of the earth and put it on the moon, what's going to happen? Can you tell me? Exactly. The water is going to boil away almost instantly because the pressure is very low, and we know that when the pressure is low, the boiling temperature gets low. Like when you go to the mountain, it's not 100 but it's 80 degrees. So if we pour all the water, it's going to boil straight away and fly away. So we need correct gravitation. Why this is happening? Because as I said to you in the last lecture, kinetic theory of the heat, the molecules are moving very fast. See, faster than the speed of sound. And now when they get out of the water, if there is not enough pressure, they'll fly away. So we need enough pressure and enough gravity to keep them, otherwise they'll fly away because of the space. This is why in our atmosphere we don't have hydrogen and we don't have helium, because they are very light gases and they fly away in the space. So this is why we need the correct sizes, and we can see how all the things in nature are interconnected, and that's very important, and that's another evidence that God created everything with such a love and such a care. Because if the gravity was much higher, then the life couldn't exist like it is now. Can you imagine? We would have weighed, say if the gravity was much higher, much more than it is, and we have to just crawl down on the earth. So the life wouldn't be possible like we know it. Tall trees like it is now, like they are now, wouldn't exist. They couldn't get so high, and many other things. If the gravity was low, the water will boil easier in the lower temperature, you see. So it's not only the water cycle and the water qualities that we're discussing, but it's always interconnected, you see. So you need to create a perfect planet at the perfect distance to the sun, with the perfect size, the perfect temperature, with the perfect greenhouse effect, so it's not going to be too much, not going to be too low, and then you're going to have water, and then you're going to have life. You see how important we to understand that phenomenon. Did you ever think about how the ice skating is possible? What makes the ice such a substance that can get slippery, and then we can enjoy ice skating? What's happening is, as you know, when the pressure is rising, the water gets from solid, it gets liquid. Look at the diagram. See, when we got enough pressure at the same temperature, the water will get liquid. The same temperature, we got more pressure, then the water will get liquid. And this is what's actually happening at the ice ring. Now, the ice skates, look at it, they exercise very high pressure on a very small surface. Pressure is force divided by area. And now when we've got, like, say, 50 kg person, you can divide it to, say, 20 square centimeters. I don't know exactly how many square centimeters you got the touch with the skates, maybe less, and then you can see the pressure is above the point where the ice now turns from solid to liquid, and this is why it became slippery. Now this is the ice skating. Now think about also the glacier that I showed you the previous time. Now what's happening with this glacier and why the glacier is moving is exactly the same while we've got ice skating. What's happening is the pressure of the ice, when it goes into the rugged rocks, they are not smooth and polished, when it gets into the rocks, get melted, and this melting makes the ice slip. Look, this is not rushing into the water with such a speed like we're ice skating, but slowly and surely it goes into the lake or the ocean or the whatever is there. So this is again the same reason why the glacier actually goes into the lake or into the ocean. Actually, this is why the glacier is actually moving. So this is the phenomena of water, which shows us how, when we have applied high pressure, the water turns from ice to liquid and becomes slippery. This is actually what's happening here. Now, I want to ask you, have you been leaving a glass of water opened and leave it at the counter and forget it, and you can see it's not going to take hours, but maybe you can take days. You can see that the water is reducing its level, is getting smaller and smaller and smaller. Why this is happening? Now, say for example, if you leave another glass of water with a lid on top of that, even the toddlers know that the water is not going to evaporate. Why it's not evaporating, and how this evaporation and how this process actually is happening. Now look at what's happening. With the closed glass, we've got two processes. One, we've got evaporation, and another you've got condensation. That means the water goes from gas to liquid. And we've got constant exchange of the two phases, liquid and gaseous, liquids and gas. Some of the molecules get too high and they go up. Some of them get slow and they return back to the water. If the lid is out, the air is going to blow them away. Even if there is no wind, it is going to disperse in the air, because all the gas substances, as we studied, try to get diffused, try to get dispersed through the space. So they're gonna get diffused. At the same moment, the molecules that get with lower speed, they're going to condense, return back to the water. And this is why all the molecules that go there come back. And it's turning like a circle. And this is why we've got the water not evaporating. You see, the water is not evaporating. Now, if we go back to this diagram, now I'd like to show something very interesting. When this vapor that we said, right, this vapor reaches 1 atmosphere, the vapor, not the water, the vapor. The water is liquid, it's fine. When the water vapor reaches 1 atmosphere, then the water is going to get boiled. Now, you should ask yourself a question when I was talking about the glass of water. Why the water is evaporating even though the temperature is much below 100 degrees, room temperature 20 degrees, 25 degrees, whatever. Why the water is evaporating? There is no 100 degrees. You can see that the boiling point, it's 100 degrees. Where is it? 100 degrees at 1 atmosphere. But why the water is evaporating when the temperature is below the boiling point? Why this is happening? As I explained to you, the kinetic energy of the molecules. Some of them get higher kinetic energy and they fly away, and then they get diffused in the air. And this is why the water gets reduced. And this is why always we have vapor pressure above the liquid, above the water. And this vapor pressure at different temperature is different. Say at 50 degrees, the water pressure is approximately 10%. See, then the water pressure, right, it gets 100% and start boiling the water at 100 degree, but it must be also 1 atmosphere. Below that, at 1 atmosphere, see, we're going to have less and less water pressure. Even at 0 degrees, look at it, there is still some evaporation going on, but it's very low. Actually, the vapor is 100% of what it is at the boiling point. Very slow, very, very slow. It's, as I say, the water pressure is 10% of what it is at boiling point. At the boiling point, we've got, when the water vapor reaches 1 atmosphere, then it starts boiling. When the pressure is 10% of what it is, you see, then we've got some evaporation, but this evaporation is with much lower vapor pressure, but still going on. So if you leave the glass there, say at 20 degrees, right, the water is going to evaporate. This is why when the rain rains, you can see on the next morning or the next day, the streets are still dry. I say, because the water is evaporating, although it's not 100 degrees. It's simply because the water vapor at this point is with maybe, say, 20 times less than the atmospheric pressure. And this is why it's evaporating much slower than if it was boiling. See? So this is the reason why we've got evaporation, although the temperature is not high, because of this water vapor. When the water vapor reaches 1 atmosphere, that means the water is boiling. But when it's less, that means the water is not boiling. But still we've got water pressure. We still got water pressure above the liquid. Now, I should not enough now to answer my question now that I would like to pose to you. Can the water boil at 70 degrees? Of course it can boil when the pressure is below 1 atmosphere. Actually, you can do this experiment at home. If you take water which is like a 70, 80, 90 degrees, place it in a bottle carefully and put ice on the top, or you just put cold water, say in a plastic bottle, the water is going to boil. Why it's boiling? Because the ice or the cold water that you're going to pour into it, it cools the water vapor, which is above the liquid, and because the bottle is closed, the vapor can nowhere to go. I actually prefer doing this experiment with a plastic bottle with tightly put cap, nicely, because this glass bottle can break. When it cools the water vapor, the water vapor actually start condensing, and that condensing, turning it to a liquid water, reduces the pressure in the bottle. And you know very well that when the pressure is reduced, the temperature of boiling is lowering. Just to let you know, 1 mole of water, 18 grams of water, and if you evaporate that, it will take 22 liters. You see that the volume of the vapor is much bigger than 2 spoons of water, 18 grams. So now what's happening when you're condensing the vapor back into a liquid, you create a pressure almost like a vacuum. And this is what's actually lowering the boiling temperature. This is why when you go on a mountain, the food to get cooked takes longer, because the pressure is lower there, and then the temperature of boiling of water, it's getting lower. Also, this explains another phenomenon maybe you're familiar with. If you've got a deep freezer say minus 20 degrees. What's happened when you close the door? It makes sucking sound. Why? Why is this sucking sound? What's happening is that, and it's also very difficult after to open the door, immediately after you close it. What's happening is that when you open the door, okay, moist air from outside goes inside to equalize the pressure. Otherwise, there is a difference in the pressure. And the air goes inside now, and now the pressure when you open the door is equalized outside and inside. When you close the door, because especially if your freezer is full, all of this is minus 22 degrees. And now when you close the door, the moist air is cooling the moisture, the gas of the water vapor. I told you there is a water vapor at any temperature. Cooling this gas, even at 20 degrees, maybe it's going to be 5% or 7% or whatever it is, this water vapor. And so it's going to go inside. But now, remember, 1 mole of water, it's 22.5 liters. 1 mole is 18 grams. That's 2 spoons. See? Now, when the air gets condensed, the moist air, that means the water vapor gets condensed, it turns to a liquid, so it takes much less space, but it creates fall in the pressure. This fall in the pressure creates this tightening of the door that you can't open, and this is why it creates this sucking sound. Are you following me? Because the gas vapor takes much more space than the same molecules will take if they're in the liquid form. So this is why when they get reduced to a liquid form, actually the pressure falls down and it creates under pressure, and this is why it's very difficult to open the door. Now let's look at the reverse process that we also experience in the kitchen. What will happen if from the liquid phase we turn into a gas phase? Same molecules. What's going to happen? The volume is going to increase. Now the volume decreased because from the gas phase in the freezer we turn it into a liquid phase, so we've got under pressure, and then we've got this tight closing the door and this sucking sound. Now what's going to happen if the reverse happening? From the liquid it turns to a gas. Obviously 18 grams per mole water, every 18 grams of water is going to turn into 22.5 liters. And what's going to happen is this is going to increase the pressure. And this is what's actually happening in the pressure cooker. Every mole of water turns into gas when it starts boiling, right? And it starts boiling and it turns into gas. So it increases the pressure. When it's increasing the pressure, what is happening? You can tell me. When it's increasing the pressure, we have this phenomena of increasing the pressure. When the pressure is increased, look at it, right? We're increasing the pressure, then the boiling point is increasing. So now we've got higher boiling point, which is exactly what we see in the pressure cooker. The pressure is increased, the boiling point is also rise to 120 degrees, and this is why the food gets cooked much faster. Now you may think about the water. We saw that it may get boiled in a microwave with much high temperature because there is no bubble sites where it can start bubbling, and then after, if we take it out, if we move it, it can burn us actually. This is why it's very dangerous to boil water in the microwave. Now I would like to ask you another question. This is called superheated water. Is there water that can be liquid at atmospheric pressure below 0 degrees? And it turns out, yes. How did it happen? Because again, when you start cooling the liquid, and especially if we take distilled water, pure distilled water, that means there is no anything that is dissolved in that. Not tap water, it must be distilled water, and we slowly reduce this temperature. Look at it, what's going to happen. This is super cooled water. It's below the freezing temperature, but it's still a liquid. To get it to freeze, I just need to give it a little nudge. That's really cool. But what's going on here? Well, if the water is cooled to below 0 degrees, it will freeze at some point, but the formation of ice crystals takes some time, and the crystals form more quickly if there is a surface on which they can aggregate, like this. Watch how fast this ice will form when I drop this into the cooled water. This is just absolutely beautiful. Nudging the bottle introduces bubbles and other imperfections into the water, and these acts as the surfaces on which the ice crystals can form. Another cool thing about super cold water is that its temperature goes up when it freezes, because freezing is exothermic. That means it releases heat. Look at it also, if we pour such water over just little bit ice so that you can start the process of crystallization, it makes like big stalactite up, going up, 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 up. So that's also, we can see another phenomenon of water. As we need a boiling sites on the superheated water, also we need a little sites on the freezing point, below the freezing point, when the super cooled water can start freeze. Otherwise it's not going to freeze until obviously it gets very, very low temperature. But you can see it's below 0. We can have super cooled water as we can have superheated water. Now, if that wasn't enough, that phenomena that we studied now wasn't enough, now it comes another phenomenon that maybe you didn't know. It's called latent heat of water. Now look at it now. There is the energy that we need to add, and there is the temperature. Now look at it now. If we take piece of ice at minus 18 degrees and we're adding energy, that means we're putting more heat into a system. Obviously, we're going to destroy some of the hydrogen bonds, and then after the water is going to reach 0 degrees, and at 0 degrees most of the hydrogens get bonds get destroyed. This takes much less space and they turn against each other, then we got liquid. Then we're adding heat. We're adding heat at 0 degrees. We still need to add more heat until the ice completely melts. And this is called the latent heat of fusion there, because we need to add heat. It's not enough to reach 0 degrees. We need to add more to destroy all of these hydrogen bonds. Then when all the ice gets destroyed at 0 degrees, then it starts rising the temperature. See, then it starts rising the temperature. And when it rises the temperature, you see, we're adding energy, it rises the temperature. We need to add approximately 4,100 joules to increase the temperature of 1 kilogram of water with 1 degree. So that we can add 2,000 joules, it's not going to rise. We need 4,000, then it rises. So we need a lot of energy to move. And this is called latent heat. Then it reaches the boiling point, 100 degrees. And the water now starts bubbling. Small bubbles. Small bubbles getting you can see, but it's not boiling completely. Now what's happening at this stage? The hydrogen bonds of trigonal pyramidal shape of the water molecule, they still exist. They get created, and they get destroyed very quickly because it's not like a hexagonal shape, sturdy. Now they're rolling against it, but still exist. So now we need to add more energy to break all of this vapor, to break all of these connections, and to turn the water from liquid to vapor. Now, looking at this diagram, I'd like you to ask me to answer the question. When do you need more energy? From 100 degrees until it is completely evaporated, until we turn it completely to a vapor, that means nothing left in the pot, or from 0 degrees water, not ice, 0 degree water, to 100 degrees. In which case it takes more energy. As you can see on the diagram, it takes actually more energy to turn the water from boiling to evaporate all the water because of the latent heat of evaporation. See, you can see also the latent heat of fusion is much less. Why? Because it doesn't destroy completely the hydrogen bonds. It destroys the structure, but still keeps the hydrogen bonds. While here, you can see there is no hydrogen bonds. The molecules fly. While here to here, there is still some hydrogen bonds existing. And this is why the latent heat of fusion is much less than the latent heat of evaporation. And that's very important and has a very serious consequences in our daily life. Now there is another question for you. What is more painful? To get burned by 100 degree vapor or 100 degree water liquid? I'll repeat. What is more painful? To be burned by 100 degree water vapor, 100 degree, both of them are the same temperature, or 100 degree water liquid? Look at it, the diagram, and answer the question. Definitely the vapor will have much more energy. Look at it, it's here, while the 100 degree liquid is here. See, it's not yet vapor, but while the 100 degree vapor is here. So now it got much more energy. Look at it, all of this distance is so that it's going to deposit much more energy on your skin, and you're gonna get burned, much painful, because you've got much more energy. All right, then another question. Can the water at atmospheric pressure, all right, at atmospheric pressure, be at 100 degree but not boiling? Yes, it is possible. Now look at it. Now there is a pot. In the pot we've got boiling water, you can see it, and then after you've got jars, and these jars inside you've got water. Now if you measure the temperature of the boiling water, it's 100 degrees. But why the water is not boiling? Why the water is not boiling in the jars? That's my question. Very simple. Because of the latent heat of evaporation. So what's going to happen is the water is getting 100 degree there. It's 100 degree there and it's 100 degree there. But here doesn't give it enough energy that is needed to start turning into the vapor phase. So the water is here now, right? The water is boiling in the pot. It may be, going into the vapor phase is fine. But now when it's into these jars, what happens is that the water cannot go over 100 degrees and stay liquid. It must be vapor. So the water is evaporating in the pot, but the water stays 100 degrees, so it's missing this phase, latent heat of evaporation, because it can't give it enough energy simply because the water in the pot reaches this point and flies away. But the water in the jars, right, reaches 100 degrees, doesn't have latent heat, and this is why it's not going to evaporate. This is why, if you can see, some people make conservation of food in these jars, me too, and you'll never see them boiling. Well, you can see the water boiling, and if you put a thermometer on both, you'll see that both is 100 degrees, but because of the latent heat, that's not happening. That's another miracle of water, that actually water, when it starts boiling, it actually disinfects and sanitizes everything, kills bacteria, so it's not harmful. And this is why boiling surgical tools is very important. Disinfects them and makes them ready for the operation. Same thing with the food. Boiling with the jars kills the bacteria that may damage it and spoil it, and makes it nice for consumption. So you can see another miracle which God created to prevent us getting sick. Later we're going to study another way of preserving food, again connected with water. Now we said that because of this high latent heat of vaporization, we've got a lot of energy we need to add until the water the water vapor gets into 1 atmosphere pressure, so it starts boiling. Well, because of this high heat of vaporization, it requires a lot of energy, definitely. You saw it by yourself. Otherwise, even in the pot, you can boil it all the day, the jars will never lose water. So we take a lot of energy to convert it from liquid to a gas. This is very important, especially in the hot weather, for cooling in living organisms, in plants and in animals, in humans. And this is very important for regulating the body temperature. This is why we sweat. And also, not only that, this high latent heat of vaporization is also important for weather patterns. Now look at this guy. He's sweating, and the water vapor is going out of his head. Actually, what you see here, this smoke going out of his head, is not actually the vapor. The water is actually condensing when it reaches the cooler air outside of his head. So now it's turning into small water droplets. We discussed that before. So the water is actually, because of this high latent heat of vaporization, it's crucial to regulate the body temperature through sweating. When sweat evaporates from the skin, what's happening? It absorbs a significant amount of heat, the heat of vaporization that we said from the body, and thus when it absorbs the heat, it cools it down, and this is why we maintain a stable internal temperature. This is called evaporative cooling. When the water first the sweat gets into our skin, it gets into a high temperature and starts evaporating. When it evaporates, it cools us. Now, if we take alcohol, medicinal alcohol, and rub it into our skin, you can see that quickly we're gonna feel a cool sensation. Why is like this? Because ethanol, which is the alcohol, ethanol has much lower heat of vaporization, not that big like we saw it in the graph. It's much lower heat of vaporization. That means takes much less energy to turn it from liquid to vapor phase, and it evaporates more easily. This is why I wonder, since I was a child, why when they did the vaccination, when they rub us before that to sanitize the place, right, with some cotton dipped in a alcohol, I feel immediately slightly cool. Right. This cooling comes because ethanol vaporizes very quickly. It doesn't have such a high latent heat of evaporation. And when it's out, it took all the energy that was in my hand. And this is why I feel cold now. Now, if we were driven by not water, if our life was based not on water, but on ethanol, then it will lead to much drastic temperature fluctuations, and that may kill us. And thanks God it's based on water, not on ethanol, simply because this drastic temperature can kill us. And now you see the temperature is keeping constant because of the higher latent heat of vaporization. That's another miracle of the water, another wonder of the water, which God created so that life can be comfortable to us. And that's another evidence and another proof of a creation, that things didn't happen just by chance. The things, you can see, it's finely tuned. When the organism sweats, or when they evaporate the water, what's actually happening? Let me show you this. The vaporized molecules carry away heat from the body. Now, when it carries away heat from the body, definitely the body is going to get cool. But because of this high latent heat capacity of water, the organism can cool itself down without losing too much water. So the water heat capacity, as I said, it's 4,100 joules per kilogram. So that means we need to add 4,000 joules to rise the temperature of water 1 degree. So that it means we need to add a lot of energy until the water starts rising the temperature. The same way now, when we sweat, what is happening? Look at the diagram. Let's look at the diagram. The water droplets that are the sweat droplets that are on our skin. The water molecules get heated by the warm skin. So what's happening? They draw heat first from the skin. When they draw heat from the skin, they start moving faster. The high speed molecules leave the droplet. Now, when they leave the droplet, the average speed of all the molecules get reduced, because now if we had 1,000 molecules, say for example, and 2 of them are moving with 1,000 meters per second, and the average speed is say for example 700 meters per second, and 2 of them with the higher speed of 1,000 meters per second leave that, then the average speed is going to go down, because we've got not 100 molecules, we've got 98 now. And now when the average speed of these droplets get reduced, it's reducing the temperature, simply because of what David did, discovered the kinetic theory of heat with rubbing these 2 ices that I said to you. So when we've got less speed, we've got less temperature, we've got lower temperature. I'll repeat again. Heat is drawn from the skin, goes into the droplets, increases the average speed of all of them, but the average speed is average. Some of them are higher, some of them are low, with lower speed. The higher speed start leaving the droplet, and because they start leaving the droplet, the average speed is getting lower, and this lowering the average speed means reducing the temperature. Now you may wonder also why our body temperature is 37 degrees. Why it's like this? God created it, our temperature, to be 37 degrees, so that when we absorb more energy with the food, right, we can convert this energy to heat and release it to the surroundings. Now, if outside is pleasant temperature like 25, 23, our temperature is 37, and outside is 25. So what's happening? From the high temperature goes to the lower temperature. See, this is the second law of thermodynamics. The temperature always goes from the higher state to the lower temperature, and our body gets cooled. So we eat more than what we need, and the energy is turned into a heat, and the heat gets released, so we get cooled. This is why it's very uncomfortable when the temperature goes above 30. So what's happening there, this cooling cannot happen so much, and we start feeling very hot because 37 to 37 is balance. 37 to 30, not so much. So we're looking at lower temperature, and then our heat, body heat, gets released. This is why we don't feel comfortable with temperature above 30. Now, what is humidity now, and how it contributes into the whole experience of having experiencing hot weather. Remember what I showed you with the glass. Some of the molecules are leaving the glass, and some of the molecules of water are returning back. See, but now if we've got more condensation than evaporation, then this is going to be a problem. This is going to be a problem. Actually, the humidity is going to be a lot of. But if we've got more evaporation, then we've got condensation, then it's okay. The water gets out. Now, if we've got the same, that means the percentage of relative humidity in the physical terms, it's 100%. That means 100% of the molecules go back. That means if you put your washing outside, it will never dry. And that's happening in the places like Richards Bay. You've seen that, especially in the moist summers. The water molecules are leaving the washing, but same molecules and the other ones are coming back. And this is why the washing never gets. That's a relative humidity of 100%. If the evaporation is more, that means we've got a relative humidity of less than 100%. We've got evaporation more, the washing is getting dry. But if we've got more condensation, that means we've got some water source from outside the washing that goes into the washing, and then after actually the washing is gonna get wetter than we put it. Can you imagine? But that doesn't tell us too much about how we're gonna feel. The humidity, actually the humidity that's reported in the weather forecasts is something else. That is how many percentage water vapor is in the air compared to the maximum amount of at this temperature that can take. So what is happening is, if the water vapor is not saturating the air to the maximum, that is kind of okay, then it's less than 100%. The lower the percentage, the better. And the higher the percentage, the worse. It can be 25 degrees but can feel like 30 and more simply because high humidity. That means that the air is super saturated with water. And why that's happening? Why that's happening? Why we feel totally uncomfortable? The sweat doesn't evaporate as easily as possible and as readily. And actually we are trapped in the heat. And making the body feel warmer, it's like in the hot weather, it's actually this high humidity works like instead of taking your clothes out, you're putting more clothes and you're trapping the heat inside of your body. It's terribly uncomfortable. While the low humidity, when the air is not saturated so much up to the it's way below the maximum, then the body can releases the heat, and now it makes the same temperature actually feel cooler, much comfortable. Also, this latent heat of evaporation helps us greatly in cooking. Why? And this high heat of water, heat capacity actually of water actually help us first even cooking. Now when water starts boiling, it actually starts boiling slower, but now once it's heated, it maintains constant temperature, and this allows for the even cooking of the food that we're going to prepare. And this is also very important for the food that we eat, simply because it keeps the food warmer after it's being cooked. Can you imagine the water to have much less heat capacity? So your wife, your mom makes your food, puts it on the table, and is getting straight cold. Totally unpleasant. Can you imagine the nice pizza or a nice spaghetti? You're putting it there, it's finished, it's cold. That would have been if we have ethanol instead of water, but we got water for cooking. And now it's slowly releasing the heat. It slowly heats and slowly releases because it have high heat capacity, one of the highest actually. And allows for also the food to stay warmer and to enjoy it. And it's also when we cook food with water, when we boil food, and like say for example we would boil different ingredients and we're putting them one after another. Now it results, instead of when we're putting the other ingredient, immediately the water to loses its heat capacity because it's very low, to lose its temperature. Suddenly the water keeps a lot of energy without losing the temperature. So now when you put another ingredient, the water doesn't get straight down to a cold temperature, then you have to boil it again. Now when you put ingredients, because of the high energy heat capacity of the water that already have, it doesn't get so much time until these ingredients that you're putting again get into the same temperature. That's very, very important. It allows to even distribution of the heat, so that all the ingredients what we're gonna boil is going to be nicely, evenly cooked. That's another incredible property. Also, if you say, if you fry some food in oil, they can get scorched and they can get burnt easily, especially because the oil doesn't have such a high heat, high latent heat, and doesn't have such a high heat capacity. So it will burn the food much easier in oil than in water. But let me show you this video about how you can cook without boiling. So let's have a look at this video. It can teach you a lot of using the principle of high heat capacity of the water and high latent heat. Now let me teach you how to save money on cooking now and to cook very quickly. This macaroni has been cooked for 2 minutes. First boil the water, then you throw the macaroni wherever you want else, and then just let it boil with the macaroni for 2 minutes. See, after 2 minutes, okay, take it out of the stuff. Take it out of the stuff, and then we need to preserve the heat. How do we preserve the heat? By isolating it. And because the water has such a high heat capacity, it will hold to its temperature for very long, and we're going to help it with covering it with a blanket. I throw 2 thick blankets on top of that. That was lunchtime. Now next day for breakfast, as you can see, it's still dark. They're already cooked, nicely cooked and warm. I put some tofu there. I don't eat cheese. And put some oil. I'm gonna put a little avocado also. As you can see, fully cooked and nicely. All the nutrients are preserved because we didn't cook it so much. So it's not only quick, but it's also healthy and delicious because all the starch is converted nicely. So how to do the beans? First thing, soak it to get out the things that are not digestible. Soak it overnight, throw the water, wash it again, put water, let it boil in the pressure cooker, and just until it's boiled. You don't need to boil it for minutes, just until it's boiled. Then cover it again around the pressure cooker like I did with the pot with the macaroni. Cover it with blankets, leave it overnight. In the morning, check up if it's soft. If it's not soft, do it one more time. It's just like a slow cooker. You just doing it with pressure cooker and with blankets. Then when you leave it one more time, check it up. If it's soft, it should be soft. If it's not, leave it again for another 12 hours. And then prepare carrots, onions, one grated potato. Boil it a little bit. You can put some oil because the water is not going to rise temperature more than 100 degrees. So the oil is not going to get denaturated. It's not going to get bad. And the beans should be ready then. Mix what you boil, your carrots and everything that I said to you. Mix it together. You can put also tomato if you want. Mix it. All of this. Put paprika. Everything. And just boil it for 5 minutes. Put thyme, spice. As I said, you can put tomato sauce, everything. And let it stay like this. You don't need to boil it. You just let it stay there for 2-3 hours to mix nicely and to all the spices to get into the beans so that it's delicious. I put potato, grated potato, because it thickens. All the consistency gets thicker. Some people put flour. Better to put grated potato. It's delicious. Enjoy it. Also, water acts as a coolant in a lot of systems, including the cars, the car engines. Also, of course, you need to put some antifreeze. So what's happening is it cools the engine, prevents it from overheating, and also regulates the earth climate. Gonna go now. And it's also used in thermal heating. Here in Africa we don't have this problem, but in Europe a lot of people use thermal heating based on water vapor, because it's boiled in one place, the heat is transferred to another place, and then it releases the heat, and inside the radiator it feels warm, nice, because that simple high heat capacity. The water actually stores heat. It's a heat sink. It's a heat bank. You can store actually energy there and release it whenever you want. Now, this is a place where I live, just 10 minutes walk from my house. And living in the coastal area, it's very got very significant points. The water ability to absorb and release heat slowly helps moderate coastal temperatures and preventing extreme swings of temperature. Oceans actually absorbs solar radiation during the day and releases during the night, creating more even temperature. And that even temperature is very characteristic in these coastal areas. And this is also very important in the global climate patterns. So what's happening with the water? Now let's see how the water moderates climate. Now, the water absorbs heat, right, from the air, which is hot, and hydrogen bonds break, right. In this way, the water actually stores the heat. Now, when it comes to that, the water releases this heat that's stored to the cooler air when the air is cooler, say at night, and the hydrogen bonds now form. So with the forming and destroying the hydrogen bonds, this is how the water regulates its heat capacity, how it stores heat. And because of this high specific heat, this absorption and release of heat from the water only slightly actually rises its own temperature, because it breaks the bonds and combines the bonds, but the temperature doesn't rise so much because it takes a lot of energy to move it to the next degree. And this is why the coastal towns normally have very milder climate. Look at it now. The land has much less heat capacity than the water. So it heats up and releases the energy because it cannot store it, doesn't have heat capacity. Where warm air rises, the rising air then form clouds because it gets cool moisture, then moves it to the sea, which is getting cooler because it's getting high, moves it to the sea, the cooler air sinks, the sinking air spreads around the surface of the water, but the ocean is cooler, so now more denser it goes as a sea breeze to the land. So look at it now. The warm air is rising because the land doesn't have strong heat capacity. It's small heat capacity. The warm air is rising. The pressure from the low is getting high. When it's getting high because it gets cooled, the cool air falls down, and because here the pressure is high and here is low, the pressure always goes from high to low pressure, and it moves the air. Now we feel breeze. What's happening at night? At night the land gets cool much faster because it has low heat capacity, cannot hold the heat. So now the sea is warmer, the warmer air is rising, it gets cooled, and then because it gets more denser, falls down, and then we've got cool breeze because the pressure now here is higher and goes into the sea. Gets warmer and that goes to the land. Gets warmer, goes to the land. Warms there, the air here goes back to the sea, gets as a cooler air, goes back to the sea, warms, and this cycle continues at night and at day. So that's what it is. Now look at the pressures now. First the land gets low pressure because the air gets heated, and when it's heated takes more volume, right? The molecules moving faster, they take more volume. It rises up because it's less denser, it goes up, it cools, gets with high pressure, then it moves. When it moves, it gets into a lower pressure, right? It falls down, again gets heated, then it gets low pressure. It falls down, gets high pressure, and when it's high pressure, yeah, again, because it's cooled by the sea, then it was with little bit high temperature. When it goes down, it cools, so it gets high pressure, and then it moves again to the land. So in this way, we've got this circle going around. And this is it's very important to how we perceive it. And these circles actually. During the day, the warm air goes from the land and the cool air comes from the sea and cools it. And at night, the warm air goes into the land and warms it, makes it the coastal areas best and perfect for temperate, nice living. So, in this lecture, we learned a lot of the thermal properties of water, and with this lecture, we're going to end our discussions about the thermal properties of water. We're going to continue next time with different properties, again amazing properties of water, which maybe you don't know, maybe you know, maybe you have to revise. But as you can see, it is so important for regulating not only the coastal areas, but global climates. Now, just imagine Gulf Stream. Gulf Stream comes from the warm Atlantic waters near the Americas, moves to Norway. And this is why we've got Narvik in Norway all around open for ships. It doesn't freeze. You've got so much high water. This you've got Great Britain, you've got England, you know, and Great Britain, UK, you've got where is at the same latitude as say Germany and Russia and Poland, but UK got much milder climate than Russia, say for example, or Poland or Germany, simply because the Gulf Stream warms it. Right. So at globally, this is why we've got also this high heat capacity of water. You can see that helps global climate nicely distributed. And it's not only that, 2/3 of our Earth is water, so it helps keeping the temperature more or less moderate. So this is the heat capacity, the latent heat, and also the different combinations of pressure and temperature of water makes it such an amazingly designed liquid and substance worth studying. And I encourage you to go